We're learning more details about 6 people killed in an avalanche near Lake Tahoe.
The mountain looked stable. The slope had held snow all winter. Tracks from earlier riders cut across the face without consequence. And then, in less than 5 seconds, the entire mountainside fractured like shattered glass. A crack shot across the snowpack faster than a human can run. The surface dropped. The slab accelerated. What had looked solid became fluid, and in that moment, geology took over. In February 2026, a massive avalanche tore through backcountry terrain in the Sierra Nevada near Lake Tahoe, killing multiple experienced skiers during a period of extreme avalanche danger. It wasn't random, it wasn't unpredictable, and it wasn't just a snow event. It was a geological failure, a slope-scale collapse driven by structure, layering, gravity, and the hidden mechanics of mass wasting. When most people think of geology, they picture magma chambers, earthquakes, and towering volcanoes. But avalanches are part of the same system. They are gravity-driven slope failures. They obey the same mechanical laws as landslides and rockfalls. The only difference is the material. Instead of soil or fractured bedrock, the slope is built from snow. Layered, compacted, stressed snow that behaves more like sedimentary rock than powder. To understand what happened in the Sierra Nevada, you have to start with a basic geological principle. Slopes fail when resisting forces are overcome by driving forces. Gravity is always pulling material downslope. Friction and internal bonding hold it in place. When those bonds weaken or when the load increases beyond what the slope can handle, failure occurs. That's true for a cliff face collapsing into the ocean. It's true for a hillside sliding after heavy rain. And it's true for a snow slab breaking loose under its own weight. Snow is not uniform. Every storm deposits a new layer with different characteristics: density, crystal structure, moisture content, temperature profile. Over time, those layers metamorphose. They bond, they weaken, they reorganize. Under certain conditions, a buried weak layer forms, a fragile zone beneath a cohesive slab. That configuration is geologically unstable. It's equivalent to placing a sheet of glass on top of ball bearings. In early February 2026, a series of intense Pacific storms slammed into California's high country. Atmospheric rivers delivered heavy snowfall at rapid rates. Wind transported snow across ridgelines, loading leeward slopes unevenly. Temperatures fluctuated, creating density contrasts between layers. From a geological perspective, the mountain was being rapidly overloaded. Each storm was adding vertical stress to an already complex snowpack structure. And then came the trigger. Here's what makes slab avalanches so geologically fascinating and deadly. The weak layer may be widespread and continuous across an entire slope. When a localized stress exceeds its shear strength, a fracture initiates. But that fracture doesn't stay local. It propagates. The slab detaches across hundreds of feet in milliseconds. What looks like a small disturbance becomes a slope-wide structural failure. Think of it like tectonic rupture on a miniature scale. A crack forms, energy releases, a plane of weakness becomes a sliding surface. The slab accelerates downhill, breaking into blocks, then fragments, then a churning mass. Within seconds, the snow behaves like a dense granular flow, capable of reaching speeds exceeding 60 to 80 miles per hour. At that velocity, it has the force of a moving landslide. This is why avalanches belong in geology. The Sierra Nevada is particularly prone to these events because of its geology and topography. Steep, glacially carved cirques and bowls provide ideal starting zones. Angles between 30 and 45 degrees are mechanically optimal for slab release. Steep enough for gravity to dominate, shallow enough to accumulate significant snow depth. The range's orientation relative to Pacific storm tracks enhances rapid loading during atmospheric river events. Wind redistributes snow, building dense slabs over weaker layers. But here's the deeper geological insight. The mountain range itself is young in geomorphic terms. The Sierra Nevada has undergone uplift, faulting, and glacial sculpting that left behind dramatic relief. That relief creates gravitational potential energy stored in every slope. Snow merely adds seasonal material to an already primed system. When the February avalanche released, it wasn't just snow sliding downhill. It was gravitational energy converting into motion across a pre-engineered terrain shaped by millions of years of tectonics and glaciation. There's another misconception worth dismantling. People assume avalanches happen because someone disturbs the slope. But the disturbance is rarely the root cause. It's simply the final straw. The slope was already unstable. The weak layer was already stressed. the additional load from a skier or snowmobiler may only represent a tiny fraction of the total mass involved. The mountain was already at its breaking point. And this is where geology becomes predictive. Avalanche forecasters analyze snow stratigraphy the way sedimentologists study rock layers. They dig pits, they examine bonding, they test shear strength, they evaluate density contrasts, they identify persistent weak layers, buried surface hoar, faceted crystals, depth hoar, that function as structural discontinuities. These discontinuities are geological planes of weakness, no different in principle than faults or bedding planes in sedimentary rock. When heavy storms rapidly load those weak layers, the factor of safety drops. The slope approaches failure. Add wind loading to create thicker slabs. Add temperature gradients to preserve fragile crystals. The system becomes metastable. In the days leading up to the Sierra Nevada avalanche, avalanche danger ratings were elevated. Forecast centers warned of widespread persistent slab conditions. That term, persistent slab, is key. It means the weak layer is not localized. It spans entire aspects of terrain. That means failure potential is large scale. Now consider this. The deadliest avalanches often occur not during the storm, but shortly after. Why? Because during heavy snowfall, visibility is poor and fewer people travel in the backcountry. After the storm clears, skies open, powder conditions look pristine, and human traffic increases. But the slope hasn't stabilized yet. The snowpack is still adjusting to new loads. Bonds are still reorganizing. The system remains primed for release. Geologically, this is analogous to an earthquake sequence. Stress accumulates quietly. When rupture happens, it can propagate across vast areas because the stress field was already critical. The Sierra Nevada avalanche was described as one of the deadliest in decades. That fact alone should reframe how we think about avalanche geology. These are not rare anomalies. On average, 25 to 30 people die in avalanches each year in the United States. Most incidents occur in the backcountry, beyond controlled ski areas where explosive mitigation reduces hazard. Colorado, Alaska, Utah, Washington, all are high-risk states. But the mechanism is consistent nationwide. Steep terrain, layered snowpack, a weak interface, rapid loading, trigger, failure. There's something else that makes avalanches uniquely geological. They reshape landscapes. Large avalanches strip vegetation. They carve chutes through forest. They transport debris downslope. Over decades and centuries, repeated avalanche paths create linear clearings visible from satellite imagery. These are geomorphic signatures, long-term records of recurrent mass wasting. In some alpine valleys, avalanche deposits contribute to alluvial fans. Snow entrains rocks, soil, and trees, delivering them to valley floors. Meltwater reworks the debris. Over time, avalanche activity influences sediment distribution patterns. This is slope-driven sediment transfer, just like landslides feeding river systems. And climate plays a role, but not in the simplistic way often portrayed. Warmer winters can produce heavier, denser snow events due to increased atmospheric moisture. Rain-on-snow events can destabilize layers. Freeze-thaw cycles alter bonding strength. Temperature gradients within the snowpack drive metamorphism, preserving faceted, weak layers under certain conditions. The interplay between climate variability and snowpack mechanics adds another dimension of complexity. But regardless of climate trend, the fundamental geological mechanics remain the same: gravity versus resistance. Here's what many don't realize. When a slab avalanche stops moving, the snow rapidly compacts into concrete-like debris. Air is expelled. Density increases dramatically. Survival becomes a race against time because the material sets up almost like cement. This behavior reflects granular flow dynamics and compaction physics, topics deeply rooted in geomechanics. Avalanches also exhibit internal flow regimes. The dense core moves along the sliding surface, while a powder cloud may billow above it, behaving almost like a turbulent suspension. In very large avalanches, that powder cloud can overrun ridges and travel farther than the dense core. These are multi-phase flow systems, again, a geological process. And here's a powerful framing for your audience. An avalanche is a temporary landslide made of snow. If you replace snow with saturated soil, the process would look strikingly similar. A weak basal layer fails. A cohesive mass detaches. Acceleration occurs downslope. Debris spreads out in a runout zone. The difference is material phase and seasonal recurrence. The Sierra Nevada tragedy underscores an uncomfortable truth. Mountains are not static. They are dynamic energy systems. Every winter, slopes store gravitational potential in layered snow. That energy waits for release. What makes avalanche geology compelling for your channel is that it connects directly to broader geologic hazards. It links slope stability to structural geology, geomorphology, sediment transport, and even tectonics. The same principles governing a snow slab apply to rock avalanches, debris flows, and even volcanic flank collapses. The question isn't whether avalanches are geological. The question is whether we've underestimated them as geological phenomena. If you zoom out further, you see that avalanche corridors mark zones of repeated instability carved into the fabric of mountain ranges. They are annual reminders that gravity never stops working. Erosion isn't always slow. Sometimes it happens in seconds. And that's the hook worth leaving your viewers with. The mountain didn't fail randomly. It failed exactly according to geological law. The Sierra Nevada avalanche was tragic, but it was not mysterious. It was the predictable outcome of layered snow, rapid loading, steep terrain, and gravity acting on a structurally weak interface. When you look at a snow-covered slope now, you're not just seeing winter scenery. You're looking at a stratified mass under stress. You're looking at a temporary geologic structure. And somewhere beneath that surface, a weak layer may already exist, waiting for the balance between driving and resisting forces to tip. Mountains are beautiful. They are powerful. And every winter they remind us that geology is not just something buried underground. Sometimes it's moving at 80 miles per hour right in front of us,